I'm going to describe on a pressure temperature phase diagram, and this is for water, how we can go from a liquid phase to a vapor phase without exhibiting a phase change by circumnavigating the critical point, which is this point here, is the highest temperature and pressure where we can have two distinct phases that exist in equilibrium. So two phases coexisting of given the values of the critical point for water. So in this diagram, we're plotting the log of pressure versus absolute temperature. And then on the right side, we have a piston and cylinder. And this is representing the volume of our system, but on a log scale, because we have large volume changes. And so right now, the drawing, dark blue, represents a liquid and corresponds to this point, our starting point in the simulation. And the idea is, first, that we have a region we label as a liquid phase, a region we label as a vapor phase, and a region we label as a supercritical fluid, but we don't have a boundary between these phases. In other words, this is a continuous transition if we go around the critical point. And so what I want to show in the simulation, that I can start with a liquid at this point here. I could raise the pressure at constant temperature to above the critical pressure. I could then raise the temperature at constant pressure until I'm above the critical temperature. Now I can lower the pressure at constant temperature back below the critical temperature. I could then lower the temperature till I'm near this phase envelope at constant pressure. And so I've gone from label in the liquid region to something we label in the vapor region without a phase change. Now this vapor I could condense back to liquid at constant pressure by lowering the temperature, and now I would see the phase change. And so the interactive simulation will demonstrate this a little more clearly. This is a simulation you can look at on your own online. It's on the Wolfram demonstration project, and it uses Mathematica to create the simulation. So let's look at this simulation now. So here's the interactive Mathematica simulation. I'm starting in the liquid phase with the green point, and as I raise the pressure, you don't see really any significant change in the volume. One, because remember we're looking at a log scale, and two, because liquid is fairly incompressible. But now I'm going to raise the temperature at constant pressure as best I can do. The main point is that I'm above the critical pressure. Again, we start to see some increase in volume, colored slightly lighter. Now I'm going to lower the pressure, and now we see the volume increase quite a bit more, somewhere between what we would call supercritical or vapor. Remember, there's no boundary. I said in the first part of the screencast that as the fluid gets less dense and becomes a vapor, it becomes green, but actually it's just lighter blue. And so I'm going to lower the pressure, and of course a fairly significant volume change. Now I'm going to lower the temperature, so we're in the vapor region. The volume decreases slightly, but remember it's on a log scale. So now I've gone from the liquid, small volume, to clearly much larger volume in a vapor, because this is a log scale, so the volume is much larger. And I can take this vapor now and I can go through a transition. And now we see a sharp transition, a phase change, to get back to my original liquid phase. So in one direction, this direction, I went around the critical point, and doing that, the transition is continuous. But now, if I instead cross this phase boundary, we see an abrupt transition. We have two phases in equilibrium. Can't see here, we just see the transition to go from the vapor phase to the liquid phase. So this is important for understanding the properties of fluids. The critical point is a very important property of a fluid. We have to keep in mind these phase boundaries between the regions are relatively arbitrary.